I guess we are ready. Double checking the volumes. Okay, I guess we can start. Maybe. All right, so welcome back to another episode of Data Science at Home podcast. I'm Francesco. As always, I'm very glad to have you on the show. And there is, of course, the usual invitation to the Discord channel. It's the official server of the podcast, datascienceathome.com. You will find the link in the show notes of every episode at datascienceathome.com, but of course also in the comments of this video for those who are following, of course, the live stream from Facebook, from Twitch TV, and YouTube, of course, as always. Now, there is one last thing that I would like to share with you, which is the very recent newsletter, so that you will never miss an episode whenever it gets published, and you will receive everything straight to your inbox. So, it's a way not to miss things, and of course, nobody will ever spam you. So feel free to share your email with me. The website is on Substack, so you will find the link in the show notes of this episode as together with the other ones, but it's datascienceathome.substack.com. Now, what do we talk about in this episode? Well, in this episode, I would like to speak about something that, a concept that is in fact very, very common when it comes to machine learning. It's of vital importance for machine learning algorithms, which is the concept of similarity. Now, the concept of similarity is very important because it has been applied across domains in many machine learning problems due to the fact that most classifiers work with the concept of similarity in the back end. And so it's kind of a core concept for pretty much any machine learning algorithm or model. Now, of course, the concept of similarity changes according to the data type. It changes according to the domain where you are applying this, this similarity concept. And it is something that make things look like magic, because we human beings have the tendency to understand the concept of similarity from a human perspective. So when we see two colors that are similar, we understand what it is. When we see two objects with a similar shape, we understand what it is. Probably we don't understand, or we cannot understand very easily how two vectors, numeric vectors, how similar they are. So we need to find some metrics there, and one of which is, of course, the cosine distance or the cosine similarity, that allows you to calculate in fact the angle between any two vectors. So when the two vectors are similar, well, in fact, when they are identical, it means that the angle between the two vectors, this is geometry, the theta, which is the angle between the two vectors, is very small, and so this means that you have a similarity which is very high, right? Ideally, it's 1, which means 100% similar, which is identical. In contrast, when the two items or the two vectors are orthogonal, well, then you have the maximum angle in between, and of course the minimum cosine, right? So that's a concept that mathematicians and people who understand geometry know this very, very well. It's a very mature concept, which is the cosine similarity, and that's exactly how a machine prefers to calculate things or calculate similarity whenever it has, it's dealing with numerical vectors. Now, with this concept in mind, we have been applying, the concept of similarity to many other items, many other objects and data types. For example, words. And so we have been discussing about a number of times, even on the Data Science at Home podcast, the concept of similarity between two words or two paragraphs, two sentences, even between two documents, using what we have discussed a number of times, which is the concept of embedding models. And so, for example, the concept of word embedding is something that we should be all very, very familiar with, due to the fact that the word embedding is a way to calculate, well, to transform any particular word of a certain vocabulary into a bunch of numbers, usually between 50 and 300 dimensions, depending on how accurate you would like to be. And each word is actually translated or transformed into a numeric vector. And then from there on, we ask a machine to calculate a, let's say, distance or a cosine similarity between any two vectors, right? So that's what we have been doing for so many years now. And with amazing results, I must say, because, back in the days, we were making these features, especially when it comes to linguistic and NLP, which stands for natural language processing. We were forging these features manually, pretty much manually. And so, for example, we were assessing the similarity between two words depending on a bunch of features. For example, the stem, the root, number of vowels, or I don't know, number of characters. Probably it's not that important to understand the similarity of two words, but you get my point. Like, it was very hard to find a way to assess similarity between two words the way human beings do. And how do human beings assess similarity? Well, they consider the context where that word is appearing. And so, for example, which is, by the way, the concept of how to build a word embedding dictionary, is measuring measuring the way a word appears in a particular context. Because if two words, even very different from each other, if they appear in a similar context, they're supposed to be similar or semantically similar. And these are the findings that allows us to for example, consider chair, the word chair, being similar to the word table, just because every time you speak about a chair, most of the time you're also speaking about, or you have been speaking about, a table as well, much less apple, right? So when you speak about chair, it happens more rarely that you also speak about fruit and trees and ground. So when you speak about ground and trees and fruit, you speak about all these three concepts more or less all together. And so if you were to categorize or assessing the similarity between chairs, tables, apples, and trees, well, you would know exactly where to put which word, right? So that's exactly what word embedding have been doing so far, and that works, very, very, very nice, because it's there is a very classic, now it's a classic example that is doing some algebra on words, which means that, queen and king, the queen and king example is probably a classic now, that allow one to consider, for example, the words man and woman similar to the words king and queen, because there is a gender relation that is transferred from the concept of, person to the concept of royalties or king and queen, right? So that's the way word embeddings have been applied so far. Now, in the literature, we have seen these things and this concept being applied not only to words, but, as I said, also to let's say paragraphs, sentences, even entire documents. And so, just using exactly the same concept, we have been applying this, word embedding or paragraph embedding or document embedding. If you Google these terms, you will see that there is a very interesting literature with exactly these terms that I just said. And so, for example, to conclude, document embedding is a machine learning model that allows you to translate or transform a document, for example, a text document, into a bunch of numbers, right? Into a vector. And so, depending on what's the dimensionality of that vector, but essentially once you have the representation of that particular document in numeric form, from there on is very easy for the machine because two documents are two vectors. On the two vectors I will apply the regular cosine distance or cosine similarity, and boom, I have exactly the same concept of similarity. I can measure the similarity between two documents, right? Now, if we want to make this concept even more, let's say, generic, we can move to the concept of node to vec. And this is also something that there is still quite an extended literature. The node to vec is a way to apply and assess the similarity between two nodes. And nodes of what? Nodes of a graph. So this is exactly what I'm going to discuss now, which is, in fact, it's the main topic. All this preamble, all this introduction was exactly to get here to the concept of node and the concept of graph. So why I want to introduce the concept of graph? Because, well, as you can understand, the concept of similarity is quite simplistic. When you think about words, vectors, documents, paragraphs, okay, we can complicate the idea, but when it comes to similarity among generic objects or even individuals, for example, and so let's call them nodes, it's not just the similarity between these two items or objects, but it's also the similarity of their neighbors, right? So it's also the context that these two entities are immersed in, right? And so, for example, and here we introduce the concept of homophily. Homophily means that similar nodes might be located nearby, right? Now, this is a concept that is very, very common. It comes from graph theory. It's very, very common for social networks. Social networks, for the record, it's not just Facebook. It's called the social network. But in fact, behind Facebook, there is mathematics. There is a graph where each node is a person. Yes, indeed. I'm sorry to disappoint you. We are just nodes of a network. And then there are relationships between us. There are edges that connect me to my friends and my friends to their friends, and so on and so forth. And so these connections are so-called relationships or edges of the network, define the type of relationship that is indeed established and measured between two nodes, right? Now, as you can see, this is not just assessing the similarity between me, node Francesco, and node Francesco's friend, right? Or Francesco's girlfriend, right? So it's not only that, it's the network, or well, the sub-network in which Francesco is immersed, is connected to, and the sub-network Francesco's, let's say, girlfriend is immersed into, right? And so it's the surroundings that defines the concept of similarity in a much broader way, right? It's not just two vectors that, as we said before, as we saw before for the words or for the paragraphs. This is much more simplistic. In this case, when you are considering networks, the complexity is much higher. Not only from a computational complexity, of course, but a computational point of view, but also from from the concept. It's conceptually more complex, right? So there are different types of similarity when it comes to graphs. For example, one very important is so-called structural equivalence, which means that there are, in a usually relatively large network or large graph, there are some sub-network that look alike. And so if you think about, take a large organization, right, a corporation, and if you were about to represent that large corporation, let's say 100 and plus thousand employees, right, it's something massive. Now, if you were about to represent that organization as a graph, you would find that some subgraphs are, patterns are preserved somewhere, right? Which means that you will find some subgraphs similar to some other subgraphs. And what is the subgraphs is probably some business units. So the way people or employees or hierarchical figures in the organization are connected is kind of preserved across the entire organization. And if you, I'm very sure that this is also the case for Facebook, the social network. If you look at the graph, unfortunately, we cannot look at the graph. Only Facebook can look at the graph. So this data is very, proprietary, and they don't want to disclose these things with us, though we create the graph, in fact. But that's probably another topic for another episode. In fact, this is going to be one of the next episodes with when we will speak about regulations and data privacy. But let's not divert there now. So even in the Facebook graph, you will see, I'm sure, some subgraphs that are preserved, the structure of which is preserved across the entire Facebook graph, right? And this is what it's called the structural equivalence. Now, as you can understand, you need to assess the similarity between not two words or two paragraphs or two numeric vectors, as we did before, but between two subgraphs or two graphs, right? So that's much more complicated from a computational perspective, but it's also much more powerful. And this is, in fact, the backhand and the core, the mathematical engine that is behind many solutions out there. One in particular, many concepts, of course, that are used on a daily basis believe me, in so many domains that you can't imagine. And that's the concept of knowledge graph. So the concept of knowledge graph is indeed a graph in which you have nodes that are connected to other nodes, and each relationship is defining some sort of semantic, it has some kind of semantic meaning. It can go from gender to age to much more complicated things like actions, interactions. For example, people played with Pluto, right? Or the physiological characters, for example. So the similarity of how you look like, or two people look like, right? Or the way two people behave, or the meaning of a word, or the way that word is indeed used in different languages. And you can be very creative to set and think about all the possible relationships that might be created between any two nodes. So this is in fact the concept of knowledge graph, and the representation of the knowledge graph is indeed as a graph in which all these properties of concept of similarity and structural equivalence are indeed very, very present. Now, there is a problem when it comes to graphs that it's in the real world we know when two things are connected. We do not know when two things are not connected, and that's a kind of a problem for a machine learning algorithm, because an algorithm is a relatively, I would say, stupid thing. It's not, but you know what I mean. It's something that you need to feed the model some data that are positive and negative representations of the phenomena that you are trying to model, right? So, for example, in a classifier, what do you provide? You provide, if you are classifying, things like red and blue, right? You have to provide things that are red and things that are blue. If you are classifying cats and dogs, or recognizing cats and dogs in computer vision, in the training in the training sample, you have to provide cats and dogs, right? So that the algorithm can learn from what it is a cat and what it is a dog, and make that distinction and learn the features that are indeed representative of the cat and of the dog, so that the algorithm can decide. The problem with graphs is that we don't have this. And so we only have the relationships that are visible, that are in fact part of the phenomenon that we are observing. And this means that is the equivalent of having only dogs or only cats. So the algorithm can never learn from the negative examples, because there are no negative examples. So how do we proceed with that? I mean, that's the main difficulty of having models that learn from graphs. And well, one idea is, of course, providing negative sampling, which is randomizing the way some nodes are connected. So you might provide the training algorithm a set of nodes that you know they are connected, and another set of nodes in which these connections are in fact randomized. And so if you take A and B connected to, via an edge, a relationship, you keep A and B connected if that indeed happens in the real world, in the phenomena that you are observing, in the so-called positive sampling. But in order to train the algorithm to recognize what is wrong in that particular case, well, then you break that connection. And so you provide A and, for example, connected to C, or A connected to D. So you don't provide A and B again, because that's what you know it exists, right? So this is negative sampling. Now, the problem of negative sampling is that when it comes to very large networks, it might be that you are randomizing and by chance you are actually creating positive samples. And so that's another problem, because you're creating confounding factors. So that's, as you can understand, it's not immediate to, finding an equivalent between the way you consider similarity for words and for paragraphs, and just, translate or transfer that concept to the concept of graphs. So that's exactly what I wanted to speak about. Now, when it comes to training algorithms, also there is another important limitation of this algorithm that need to be trained on graphs in which the dimensionality of the problem is usually orders of magnitude bigger than the dimensionality of the typical problems in which we deal with the words or paragraphs or numeric vectors. And so, in these cases, we might be dealing with a computational complexity that is so high that most of the time training these things on one machine is going to be almost prohibitive, which is why especially companies of the caliber of Facebook, they have been investigating, and also Google, they've been investigating methodologies that allow one to, let's say, distribute the computation when it comes to graph processing and graph training, and use other alternative algorithms or stochastic gradient descent that are in fact distributed. Now, one in particular is Hogwild. We have been discussing about Hogwild in a long time ago, actually, in one episode of this podcast. You can definitely search it on the website, datascience@home.com. And I remember that there was an episode in which I showed majority of the optimization algorithms that are out there and are currently used in not only in deep learning algorithms, but also in simple logistic regressions and the like. So Hogwild is an algorithm that allows one to, let's say, train a stochastic gradient descent in a distributed fashion. And this means that there are multiple machines doing the job of minimizing the loss function. For the record, the loss function is that function that you want in fact to minimize. It represents the differences between the prediction and the ground truth. And so if that difference is minimal, it means that the algorithm is very accurate because it gets it right? Now, how do you proceed when you have, for example, billions of nodes in a network and billions and billions of edges, of connections among these nodes? And these are really not numbers that I'm making up. These are real numbers. Imagine that, I don't know how many people are using Facebook, I believe billions. Now, imagine if every person is one node in the network, in the graph. One person can be connected to, I don't know, what's the average, probably 50, 100, maybe much, much more other people. So if you have like 1 billion users, In fact, it's much more than that, I believe. You have tens of billions of edges, right? Because every person is connected to tens and tens of other people, or hundreds of other people. So that's the idea. The thing is that when it comes to these types of problems and this dimensionality, forget about running these things on one single machine. If you move to a domain like chemistry or computational chemistry, for example, you have particles there or chemical compounds, and the numbers are very similar. You also have billions of things. And when you go to genetics, you find exactly the same problem, the problem of dimensionality. And so there is a paper that has been provided by the research team at Facebook. I will report the paper in the show notes of this episode. And it's a paper that allows you to, it's called a PBG, which stands for PyTorch Big Graph, PyTorch Big Graph, PBG. Computer scientists are always, using these acronyms, and that also put me in danger whenever I didn't prepare and understand that acronym before the episode. But I am a computer scientist myself, so I know the jargon. Now, PBG is exactly an algorithm that works on a graph. Not only that, it applies a hog-wild-like algorithm to distribute the stochastic gradient descent on a number of machines, and the way it works is very simple. Well, relatively simple. They partition the nodes into partitions, and then they maintain, in fact, partitions that are disjoint from each other, so that they can operate and train on each partition independently. And so, they spend a bit more time making the right partition, and then they distribute the computation. That's where the trick is. Spend always a bit more time, setting up the data structure, and then run the algorithm. That's very important. I don't know who said, when you run something that you want to be optimal in doing that something with computer science, devote much more time on understanding how you structure your data. And so data structures are, in my opinion, much more important than the algorithm per se. In fact, some data structures allow you to perform special algorithms or specific algorithms that are by construction faster or linear with in time, or linear with the number of nodes in this case. And other data structures prevent you from running these linear algorithms because they are not, very well designed. So that's exactly what they did at Facebook. And Facebook is, is a kind of a competitive advantage because they, first of all, they have these problems. They are born with these problems, the problem of dimensionality, but they also have the data. And so they can find, they can experiment a lot with, for example, the optimal partition that allows you to, scratch more computing time from the overall time that you need for that type of optimization. That's it for today. I think that, I hope that you enjoyed the live stream, and of course, come on the Discord channel. Let's have a chat. It's the place where you can propose the new topic that you would like me to speak about, or you want to come and discuss or ask some questions about the previous episodes. That's very fine with me. I mean, I actually have a lot of fun answering, especially smart questions. But of course, don't be shy. The most stupid question is the question that you never made. Last but not least, subscribe to the newsletter. It's free of charge. No spam included. Believe me, your email will never be shared with anyone except for myself and Substack probably. So we'll never miss an episode. And of course, tell your friends. I would really appreciate. Thank you very much for being here, and I'll talk to you next time.